It's off. It's okay. It's off. It's off. We can stay off. Are we off? We can stay off? Yes. Cool. And we are live. Is the stream is working. I think audio should be working, and the screen capture should be working as well. So, good Monday morning today. Yeah. So as you can tell from the title of the stream today. So what we're going to do today is we are going to how do I explain this? We're going to try and see if we can implement non-blocking delay, and we'll go through some reasoning for why we should do that, and of course how that should be done. So I'll just start out with a cool little example, and then we can kind of build up from there. You know, it's easier. It's easier if we use an example that we can build up from and keep going with, rather than if I just blab on and explain stuff. So usually when I start a project, when one starts a project, you're really focused on getting like the system running, or almost so getting the almost like getting your first LED to blink. Just making sure your board is okay, and you can do debugging, and you can kind of see into the system. And beyond that, you basically start from, you want to see, is my system running? Can I do stuff with it? Before you start basically diving into building anything more complicated or more built up. And usually, what I do in my systems is I will set up an LED. Like, yeah, as you see, I've set up the blue LED on the STM32 F407. And what I have there is I have a blue LED, and basically I have it set, and while one basically doing nothing, and this should basically run, our code should run. And if I am lucky, if the demo gods are working for me today, once we start debugging this code, we should, I don't know if we'll see anything, but we should see something like system has been in it. And ideally on our board, for just physical confirmation, we will see a blue LED come on. And let me see. And yeah, as you can see, there's a blue LED somewhere here on my board coming on. Yeah, there you go. Cool. So what did we just do? We used CMSIS, and we set up the LED, which is on PD15. And we set out mode for we enabled PD15. We did a mode, we did an output type, we did a speed, we did a pull up, and we did a speed, pull up, and the output type for the setting. And then eventually at the end, we turned on the LED. So let's introduce, so usually what I do is, in new systems, I will go and I'll define, let's do a void define. Let's define a delay function, void delay. Okay. It takes nothing for now, because for now we just want some crude sort of delay. Okay. Cool. Let's actually define our delay, void delay. And then in here, let's do some sort of weighting mechanism. So the easiest way to wait with microcontrollers is to do something called busy wait. And a busy wait is basically microcontroller's version of asking the question, are we there yet? So what I want to do is I want to roughly wait some amount of time. Because we are so early in the project, we do not have a definition of time yet, or rather our microcontroller does not have an understanding of time yet. So we're just working on frequencies, and basically what frequency is the system running at. And if you can see here, we are running at 16 megahertz on system init. So we know we're running 16 million ticks per second. Okay. So roughly I want to take like maybe I want to wait maybe a millisecond or so. But it's just a rough delay at the moment. So I'll do and we know we're doing maybe uh, since we're doing 16 million ticks per second, that's how many times our clock pulses per second. We want every time our clock pulses, we will our CPU will compute an instruction. So let's give our microcontroller some instructions to compute so that our microcontroller can make a delay. And in microcontroller world, this is basically the version of, I think I've said this. This is deja vu now. This is a version of asking the question, "Are we there yet?" So let's ask the question, "Are we there yet?" So, and how would I do this? I would actually have. I would just let's waste some time for uint 32 ti equals 0. So let's start at 0. I equals less than 250,000. 1, 2, 3. I plus plus. And then in here we'll basically do this and we'll do nothing. Okay. So no operation. Basically what we're asking here is we're asking, are we there yet? Are we there yet? Are we there yet? So let's actually put in printf here. So instead of actually doing a nothing, let's actually demonstrate what is happening. Printf, some random instruction. Are we there yet? Yeah. Okay. So if we want our LED to basically toggle, we want to set up the system, start the system, and then once the system is started, we want to toggle the LED on, off, on, off, on, on, off, on, off, on, off. So when we get to our while loop, let's use the delay we had. So let's remove this and then go boom, and then we'll say doom, and then we'll get in here. I think this should be there, and then we will run our nice little delay and do that, and then we'll go that, and then what I would do here is I will do bit reset bit r bit reset 50. Okay, so we have something here that actually demonstrates a busy wait. So turn on the LED, turn on the LED, turn on the LED, get busy waiting, turn off the LED. So let's see what happens here. Okay, cool. So let's stop this. Let's run it. Let's run this code and let's look at our ITM terminal and then let's just play it. Let's see. Oh yeah, cool. So what is happening? Oh, so we are getting the questions, but we are not resetting our I understand. So we are resetting our LED. However, after we reset it, we just jump back into the while and set it on. So let's add another delay. So we get an off period. Busy wait for off period. Okay, so let's look at that. So we have an LED on now, and then if I do stop, if I stop this code and then I run and I start debugging, what happens? Good, we have the code written in, and if I play, so let me go down into the my ITM console, and if I play this, we should have an LED come on. We should also have it go off. Okay, I'm doing something wrong. So, sorry, sorry. While one, turn on the LED, turn off the LED. I'll just run both this thing. Okay. Let's run this outside the loop and then run a delay in here, just so we're not messing with the loop, and we can get on. If we get an on-off, then we can go back to this and debug why that's not working. Cool. So, live development, live coding, as always. Start debugging. IDM console. Play. On off. On. Just on. Off. Does anyone see what I'm doing wrong here? Am I doing something in system init that is messing up with my LED? Yeah. Okay, cool. I was touching my LED in system init. I'm going to try it again, so it's fine. Now let's try. Run. Start without debug. Start with debug. Okay. So okay, stop. Run. Start debugging. Okay. Okay. Cool. It should come back at some point. Okay, so here's one of the problems that we're experiencing. We do not know how long this delay is going to take. And as we wait for this, we're just waiting and we'll see what happens. So let me just remove this. Okay, stop. Okay, so I'll remove that and run, start debugging. Let's see. Walk. Turn on the LED, delay, turn off the LED. Cool. So it turned out it was our instruction. Yeah. So this should be empty. This is a busy wait. We should find out why that doesn't work. Okay, cool. So we have a delay, and if we use this in our while loop, we can now have a toggling LED as our application. Cool. Okay, cool. Okay, cool. So run. So let's look. Stop. Run. Start debugging. Look at our console. I'll just play it. Okay, same issue. We do not have a delay after. So what happens is it just goes, it jumps immediately into the on one. Let's try again. Run, start debugging. Amazing. Okay, cool. We finally have a demo of our blocking delay working. Okay, so our blocking delay is working and we have a blinking LED. So here's the thing. Whenever we are blocking, as you saw just now, our process, it couldn't do anything else. You see, we could not print to the screen. We couldn't print out, we couldn't do some other operation while we were waiting. Basically, what blocking delays give us is just we have to wait. Busy wait faster. It's like we're telling imagine going on a trip with a child, and your child's sitting on in the back seat, and you're going to another city, and all your child can do is ask, "Are we there yet? Are we there yet? Are we there yet? Are we there yet? Are we there yet?" Pretty soon, it's gonna get quite It's going to get quite difficult to drive because number one, you'll get distracted. This is quite very discomforting. You're doing something that's like, you're just busy saying no, no, no. And if it was if the world was such a way that you had to answer that question every time, are we there yet? Are we there yet? Are we there yet? Are we there yet? You basically would get very distracted, and you wouldn't drive properly, you wouldn't be able to get there. And now imagine a world where you can tell your child, we're going on a trip to a different city. And she gets into the back seat, you give her an iPad or you give her a book, or you open the window for her, or you give her a puzzle, whichever way, whatever satisfies us today. And now what happens is your child will play a game, she'll do stuff, and she'll look at things. And whenever she's bored from the thing, or she's taking a break for the thing, she'll go like, "Are we there yet?" And mom or dad will go, not really. We still a few more hours. Immediately, this becomes a more desirable situation. But let's even give it an even more simplistic. Instead of your child doing something else, your child could just sleep, which most children do. They sleep, and then you sleep for a while, and then when you wake up, you ask, "Mom, is it can we go now? Are we there? Are we there?" And this translates into a 5-hour trip. You could get asked, "Are we there?" twice, or maybe even once if they sleep well enough. And that would let the driver, do more things, be more focused on the road. It would let the asker of the questions be more calm because they would be more settled. They wouldn't need to ask the question, and they know they will get there. Whenever they get there, they will either be reminded, or whenever they wake up, it's good to at intervals check. So what advantage? So I've implemented a sort of like a non-blocking API for delays, and that's what I'm going to demonstrate here so that we can see. So the first thing I did, as you can see with the open files in my thing, was I went and I declared a header. So I want to set up a maximum number of timers that I'm going to have, so that I can monitor them. This will depend on how much RAM you have. 10 is just an arbitrary number. It could be anything. And then I want to give each timer a delay counter. So that way we can spin up a timer and be like, give it some time to wait. And then once it's waiting for that time, once that time has elapsed, it will tell us, and then we'll go on doing the other stuff. We will go on with the task that we wanted to wait for. What this exposes us to is, while the timer is waiting for the delay to be done, we could be doing some other unrelated tasks, and that would help us achieve better. Okay. In the world of embedded, being able to do other unrelated tasks is massively important, and massively this is really what people need. And that's what you're delivering. You're delivering a system that can almost act as a human. And what do humans do? They can process multiple pieces of information coming at them at different times. And they can, this person just gave me this, I have to wait for something from there. I can do something else as I wait for something. Okay, cool. And then we declare an external number timer. So basically it's going to be used in these files, but it's going to be declared somewhere else. And we declare a list of timers, so delay timers with a number of max timers. So that's we have a maximum of 10. And then we have a function to initialize a timer. to initialize our timer here, the whole timer system. And then we have a function to start a timer, a single timer. And then we also have a function to check whether that timer has elapsed. And then we have a function to update all the timers. Okay, so let's go and look at let's review the code. Let's review the code for all the functions. So, and let's actually, I think, write some documentation, because that's going to be really cool. So cool. Timer init, timer init, initializes the timer function, the timer functionality for our system, for our system. At the moment, this assumes we are running at a clock speed of 16 megahertz, and we'll make Systick at the rate of once per ms. Okay, cool. So I'm kind of introducing a concept here, Systick. So I'd like to quickly use Google to see if I can find the Systick concept. From what? Yeah, what is the purpose of Systick? The main purpose of this timer is to generate a periodic interrupt for real-time operating systems. So forget the real-time operating systems. Well, if you're watching this video, then you're aware of real-time operating systems. But what do we do? What does Systick do here? It generates a periodic interrupt for a real-time system. Okay, cool. So for a real-time system, forget that. We are not yet at the real-time system, but let's go with the first part of that definition. It generates a periodic interrupt. So here, what we want to generate is a periodic interrupt at once per millisecond. So we want some sort of thing to tell us that a millisecond has gone past. Okay, once we have something telling us that a millisecond has gone past, we can now use this to, if we have information. Okay, I have a watch and it tells me if a minute has passed. If I want to wait 5 minutes, I'll just check. Every time I'll check my watch the first time and it will tell me it is 9:05. And then now in my head, I'll decide if I want 5 minutes to pass, I want to check whether it's 9:10. Okay, cool. So now every time I'll check, every 2 minutes, I'll look at my watch and I'll go, is it 9:10? Is it 9:10? Is it 9:10? So what do I have? I have a concept of time. I have a concept of when I want it to be, or I need it to be. I have a concept of when now is. So if I need to wait for a certain period, I can make the difference and then use that. Okay. So let's also document timer start. Okay, cool. So what does this do? Come on, give me a way. Okay, cool. Brief. So this is timer start. function to start a specific delay timer. Remember, recall each delay timer has a delay counter, and by starting it we assign it a number of milliseconds. Then let the Systick interrupt decrement those seconds and those ms until they are 0. Okay, cool. So what do we have here? We have a timer start function, and this timer start function will accept a delay timer. Remember, we have a delay timer from here. What is a delay timer? It's a struct that contains a delay counter. A delay counter is a number of milliseconds to delay. Okay, cool. So whenever we start a timer, we basically give the delay counter some milliseconds, and then we know once we assign some milliseconds to a delay counter, our Systick handler will do some decrementing. So let's actually look at that code right now. So let us document this like that. So timer update. Okay. Internal function consumed from the Systick handler. So basically this is run at the rate of once every their millisecond values. Okay, cool. So what do we have here? We have timer update. Timer update just makes a list and with the maximum number of timers, with how many. We take the number of timers that are available right now, and however many timers we have that have a delay counter over 0, we then decrement their delay counter, which basically makes the counters run. Okay, and then Systick here, this just handles this. Systick handler ISR for Systick interrupt. Okay, cool. And then we have a final one here. Nice. Let's look at this one. What does this do? Okay. So let's do timer is elapsed. API function to check when the timer is elapsed. When our timer is elapsed. Our timer is elapsed. Since delay timers is global, this accepts a list an index of a timer and uses that index to pick our correct timer to check. Okay, so let's quickly run through these functions again. So we have a timer init. It initializes a timer system for our basically it just starts our Systick interrupt. Okay, then we have a timer start to start a specific timer at a certain milliseconds, or rather a specific delay for a certain milliseconds. Then we have timer is elapsed, which is what we use to check whether a specific timer has run out. Then we have timer handler, Systick handler, which basically runs timer update, which decrements the timers as we go along. So let's go use this in our main and see how it works. So let's, after we do initialization, let's do here and run timer init. Cool, let's run timer init. And then in here, I want to, I already have some of this code written. And let's take that. I already have some of this code written and I just want to demonstrate. Let's see actually. So let's now here, just before our while runs, let's start a timer and then I actually want to start this timer. I want to start this timer here. I want to start it inside the while loop. And then I want to while. Let's see. I already have this code. So I'll just copy this. Forget all the other stuff. I just want to demonstrate with the LED right now. I mean, I'm demonstrating from within an actual system, so I basically deleted code to make sure this doesn't happen. Okay, cool, and I'll explain this at some point. So while time is blah 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 blah, turn off, and then I want to do the same thing here. Otherwise, we just jump back into. Otherwise, we just jump back into the other thing. Yeah, let's wait twice. Okay, cool. This is inefficient, but this is what we need to do to demonstrate. So what are we doing here? We first of all timer initialize, so this means we run the Systick interrupt. Then we declare our main timer, and then we make an index for it by increasing num timers, and then we add it to the list of timers. And then once we add it to the list of timers, we start the timer at 20 milliseconds. And then once the 20 milliseconds have elapsed, we'll turn off the LED. We start the timer, and then we actually can turn on the LED. Turn on the LED. Let's turn on the LED. Start the timer. And then wait for the timer to run out, turn off the LED, start the timer, wait for it, and then go back and do the same thing again. So let's look at if this does. So this is our old code running the old busy wait. So let's see if this one works. I'm hoping it does. Ooh, we have an error. So let me think about it. Timer init, delay timer, while timer start. I have a feeling I'm doing something wrong here. So I'll just go back to how it was. before just now. Yeah, let's do a timer X, yeah. Timer start. Okay, and then timer start. It will basically won't go on again, I think, but let's do while we basically need another one. I'll show you. So while time is elapsed, while come on, just a moment. Bear in mind, I'm trying to make a contrived example from a very from quite a an existing system. So I'm kind of stripping things down, stripping things out of. Okay, let's start with this one. Yeah. Actually, let's do all of this outside the loop so that we actually know that this kind of works. Oh my word. Okay, we'll remove that, and then I'm gonna do this outside the loop so that I don't start the timer multiple times. And then I'm going to remove that, and we're just gonna run once. I'm aiming for a short video today so that I can demonstrate that this works. So set the timer there, set that, and then I need to initialize that timer. Apologies, this is gonna take a bit of doing. This is what I want. I should control X. I don't want it there. Yes, because I am running it in system. Okay, cool. And then I want to do okay, cool. So before we go into the while loop, let's just do it out here. And then I'll do this. And then I will bit reset. Okay, cool. So this is off. Bit set. Put it on. And then I'll say while. Okay. So, and then I want to come and take my while here. I pre-wrote earlier. Okay. Control C, put it here. Where do we put it? Oh, do I have charts going on? Do I have charts going on? No charts. No charts at the moment, no questions at the moment. So I will drop this in Control C, and then I want to drop this in here. I want to come and drop this here. Okay, so let's check the, let's do this here. Okay, cool. What does this do? And then we should do that. Bit reset. Okay, cool. Bit reset. Okay, so we should definitely just get one blink here, and if possible at the rate of 20 milliseconds. Okay, it'll go on off. Okay, so that's a problem. it is not going off. I'm wondering now whether I'm setting this somewhere else. Am I using a while not? So this, you should not do this. That Ali should only start it here, somewhere like here. Let's run. I have a feeling I'm getting some data corruption because of that, but that's fine. Time I didn't need. Can anyone spot my errors? Okay, cool. So run, start debugging. We should get one single blink and that should be good. Stop. Run, start debugging. That's good. Let's look. Let's through it. Yeah, something's wrong. That's too long. I'm using the wrong timer somewhere. Just a moment. I need to see how I'm doing this in the actual system that I haven't messed up that bad. Source. All of this is on my GitHub. You should. I'll do the one linked on the stream. So you should be able to just use this at whatever time you deem fit. Why do you want me to add it before? Okay. I don't know why. I don't know why that works. Okay, cool. We are successful. Run. Start debugging. Let's see. We should get a very quick blink. Okay, cool. Run again. Run. run, run again, run, run. Basically, so what are we getting? What have we achieved really? What we have achieved is we've we've built we've built a timer. We've initialized it, and now we can do sort of sleeping wait. We are not yet at a point where we can do other tasks because look, whenever our timer is elapsed, we just sleep. Okay, so this is very good for very small. Like this is go to the definition. Okay, go. So what we have right now basically and allows us to um yeah, there you go. Wait for interrupt. Wait for interrupt is a hint instruction that suspends execution until one of a number of events occurs. So look, it goes like it's waiting for interrupt or if something reads memory. Okay. We can also have a no operation there. You see, like we can have a no or something of some sort here instead of like wait for interrupt. But what we're doing here is we are slipping the processor, and then whenever we're ready to go on, we're going on, and this gives way for like linear execution thing. So if you need to do things in a linear way and then wait for them and then go on, we have a system that can do that now, and we can do that while not busy waiting. So if we're not busy waiting, which means we can't miss interrupts, we can't miss instructions, like as you saw at the when we started, when we implemented the delay, the just printing delay that was doing something and it was waiting. It was so focused on doing that that it just corrupted everything else that we were doing because we were missing the instructions that we needed. And that is a sort of advantage that you get from running blocking time. I'm really glad it worked today. They're getting better. We're getting clearer and we're getting more concise. It's been a pleasure hosting you. If you do want to support me, please subscribe, leave a comment, or like. Join a session and ask some questions. So you can also ask some questions. I have a Discord and a blog link down below, and send me questions, and this gives me ideas on what videos to make, and I really enjoy doing this, which is super cool. So thank you today for joining me. All the code for this will be on the repository link below, and feel free to leave any questions, feel free to leave any comments, even jokes if you want, and see you next time for I think I squared C. This is amazing. Cheers.